Good evening to all our students. Thank you so much for joining us today. We shall commence our program shortly. So with your permission, may we begin the program? All right. Good evening to all our students. Welcome to your fifth and final session of the Vikram Sarabhai Science Foundation Science Promotion Orient Test. We're so happy to have you with us again today. Before we move on to our session, the housekeeping rules that I request all of you to ensure that you follow. Kindly note that questions from this session could be part of your spot final exam. All right, please ensure that you fill in your attendance form, which has been sent in the chat box, so that we will be able to mark attendance for the same. Yes, so that brings us to our topic for today, which is atomic energy. And our resource person today is Dr. Swapnesh Kumar Malhotra. There are a lot of laurels to read about Dr. Swapnesh. I will try my best to justify all the work that he has done for our country. He was the past head of the Public Awareness Division for the Department of Atomic Energy, Government of India. Prior to that, he superannuated from the Department of Atomic Energy as outstanding scientist and head for the Public Awareness Division. After his post-graduation in chemistry from Agra University in 1976, he joined the Bhabha Atomic Research Center, Mumbai. After a year training in nuclear science and technology, he joined the Bhabha Atomic Research Center as a scientific officer. For more than 2 decades, he was engaged in research and development on heavy water, an important nuclear material for the Indian nuclear power program. His major fields of interest were hydrogen isotope separation, fractional distillation, cryogenic distillation, electrolysis, metal hydrogen system, mass spectrometry, etc. He was also involved in the technology transfer activities of the Bhabha Atomic Research Center for a couple of years. Since 1999, he was the head of the Public Awareness Division of the Department of Atomic Energy, where he was responsible for planning, overseeing, and assessing the entire outreach program of the Department of Atomic Energy. His untiring efforts in creating mass awareness about atomic energy in general and uranium mining and processing in particular have been well recognized. He has produced a number of documentaries on the Department of Atomic Energy and its activities. He was also responsible for the conceptualization, design, and production of various publications of the Department of Atomic Energy. He has also served as an expert with the International Atomic Energy Agency for assessing and advising them on their public information program. Most importantly, he is very fond of interacting with students and youth, and in 2007, he was bestowed upon by the Department of Atomic Energy with Special Contribution Award for his valuable contributions in the field of nuclear science and technology and the programs for the Department of Atomic Energy. As you can see on your screen, these are just a few of the laurels that we have picked to introduce you to our speaker today. Doctor, thank you so much for joining us. Over to you.
Thank you. Namaskar, everyone. I'm really thrilled that so many students on a public holiday, they agreed to join me, and I'll share a little knowledge I have about the Department of Atomic Energy and its activities in the field of atomic energy, maybe in next 1.5 hours. So let's get going. So the topic of the title of my lecture is Splitting Atoms for the Progress and Prosperity of the Nation. Now, why we have given this topic? Though in atomic energy, we not only split atoms, we fuse them also. As you know, there is fission and fusion both. But you know, this tagline or this title I had given, maybe some of you were not even born. In 2002, we had a Vigyan rail, you know, so it was a train full of exhibition. It had 14 and one of the bogies was on atomic energy, and the then Minister for Science and Technology, Mr. Murli Manohar Joshi, he requested that everyone come out with a tagline which will be put outside the bogie. So, and it was to be given in English and Hindi both. So this, in fact, this was coined by me, splitting. So we had written Department of Atomic Energy on the top, and then below that, splitting atoms for the progress and prosperity of the nation. And in Hindi, it went like Parmanu Urja Vibhag, देश की परमाणु का विखंडन देश की समृद्धि एवं विकास के लिए. So then I am so fond of this title that generally when I give an overview of the activities of Department of Atomic Energy, I usually use this title only. So let's get going. Next slide, please. So this slide actually basically just, if I am not allowed my complete PowerPoint presentation and I am thrown a challenge that only with one slide you have to give your lecture, then this is the slide. This will be the slide which summarizes the activity of Department of Atomic Energy. In the center, you see the logo of Department of Atomic Energy. And there also it is written, Rashtra ki seva mein Parmanu, atoms in the service of the nation. Okay. And around that you see other pictorious circles. And in each circle denotes one field in which we are working. So, I mean, if you start from the right-hand side bottom and go anti-clockwise, then first one you will read is nuclear power. Okay, so that means essentially generation of electricity by putting up nuclear power stations and other things required for it, which we call as nuclear fuel cycle. So all those activities come under this. Then next is water resources. So in management of water resources, how atomic energy is used, anyway, I'll be describing in very brief. Then in healthcare, in what way atomic energy contributes to the health of the people. Then in food and agriculture, then in national security, and then research and education. So I think except for the national security, I'll be talking more or less about everything which is listed here. Okay, so can we have the next slide? So we are starting with the nuclear power. That means our electricity generation program. So let's get going. Next slide. So we start with a brief description of nuclear fission. Now I'm told you are all senior students. So I think 11th standard onwards. So I think all of you know what is nuclear fission, but just for the sake of completion, I have put the most popular fission reaction here, the fission of uranium-235. So when it is bombarded with a neutron, it undergoes fission. So it essentially breaks into two or more smaller nuclides. And then in each fission, 2 to 3 neutrons come out, and in one fission, 200 million electron volt of energy is released. Now, electron volt is a very small unit of energy, which is generally, when we are speaking at atomic and molecular level, then we use this unit. Okay, so so uranium-235, because it undergoes fission when bombarded with neutron, so it is known as a fissile isotope. Okay, because it is undergoing fission. Now, there are some other isotopes. Of course, periodic table is full of isotopes or full of elements. So there are isotopes. When you bombard them with neutrons, some other things will happen. They might absorb neutron, they might scatter neutron, they might reflect neutrons. So many things could happen. But there are certain isotopes like uranium-235, which will undergo fission. They will absorb the neutron and will undergo fission. But there are some other isotopes which are known as fertile isotopes. Why? The reason being, they themselves do not undergo fission. But when they absorb a neutron, they ultimately undergo transmutation. Okay, so essentially what happens is, for example, this uranium-238 example I have given here, when it is bombarded by a neutron, it absorbs the neutron, and when it absorbs the neutron, what will happen? It will become uranium-239. Okay, because atomic mass will increase by 1 because neutron is getting added. So it will become uranium-239, and actually that uranium-239 is not stable. So it undergoes very quickly 2 beta decays. Huh? I think you know, I'll be discussing later on, but you must have studied what is, alpha decay, beta decay, and gamma decay. Anyway, I'll be discussing about it. So beta decay essentially is a conversion of beta decay will occur only when there are excess neutrons in the nuclei. So to make it stable, what it does is that neutron is converted into proton. Now, neutron is electrically neutral. So when you convert it into proton, you are producing +1 charge. So to balance that, a -1 charge is also produced, but you don't have much mass to do that. So the particle is electron, but it is produced from inside the nucleus. So essentially, neutron is breaking into proton and electron. So this electron comes out of the nucleus, and that electron, which is coming from the nucleus, is known as the beta particle. Okay, to differentiate between this electron and the electron which is already available in the surrounding of the nucleus, in the orbits around the nucleus. Okay, so an electron, when it is generated from inside the nucleus, it is known as beta particle. So that beta particle, so one beta decay will mean that atomic number will increase by 1, because you are increasing 1 proton. By beta decay, you are converting a neutron into a proton, so the atomic number will increase by 1. Okay, because atomic number is essentially number of protons inside the nucleus. So since you are increasing the you are increasing the number of protons by 1, so atomic mass is also increasing by 1. Okay, so I was telling you that uranium-238, when it absorbs neutron, becomes uranium-239, and then it undergoes 2 beta decays. So its atomic number will increase by 2. So uranium atomic number is 92. So the new element will have atomic number 94, which belongs to plutonium. So that is how I have written here that uranium-238 is getting converted into plutonium-239. Now, this plutonium-239, it is not a natural radioisotope. It is not available in the nature. It is a man-made isotope, and it is fissile. It can also undergo fission. Okay, when it is bombarded by neutrons, it will undergo fission. Okay, so this is an example of a pair of fertile and fissile. So fertile material uranium-238, if you bombard it with neutron, you will get a fissile material plutonium-239. Similarly, there is another element which atomic number 90. That is thorium-232. Okay, so thorium-232, when bombarded by neutron, it's in a very similar manner, it will become thorium-233. That thorium-233 will undergo 2 quick beta decays so that its atomic number will increase by 2 and it will become now 92. Now 92 belongs to uranium. So you get another man-made isotope of uranium which is not available in nature. This is uranium-233, and look, even this is fissile. So a fertile material, thorium, is converted into a fissile material, uranium-233. So these two reactions, conversion of fertile to fissile, are important. So kindly make a note of this. I will be using it after few slides. Okay. So now, gentlemen, we have 3 fissile materials. One of them is natural, uranium-235. And other 2 are man-made fissile materials, plutonium-239 and uranium-233. How we make use of these 3 fissile materials, I'll be discussing after a few slides. Now, let us come back to fission. So each fission, as already written above, produces or generates 200 million electron volt of energy. Let us compare it with combustion of carbon. See, as you know, when carbon undergoes combustion, it also releases a lot of energy. So in fact, we are presently, conventionally, we have been making electricity by using all that heat which is emitted by combustion of carbon. So that itself is an enormous heat. But let us compare it, compare the two, the combustion of carbon and fission of any of these fissile materials. So for example, when one carbon atom undergoes fission, undergoes combustion, so C plus O2 giving you CO2, it releases 4 electron volt of energy, one atom. Okay, so compare it now with fission of one atom of uranium, which is 200 million electron volt. Okay, so you can see millions of times more energy is emitted by the same amount of, same number of atom, one atom. So this is essentially the advantage with the nuclear power, that it's a highly concentrated source of energy. So in using very small amount of fuel, you can generate large amount of energy. So for example, suppose we have to build a 1000 megawatt electricity generation plant. Okay, 1000 megawatt. And let us say we are going for a nuclear power plant. So if we are using natural uranium, it will require about 160 tons of uranium in a year. 160 tons of natural uranium in a year. Or if the uranium is enriched, I will, in a moment, I will tell you what is enriched uranium. So instead of natural uranium, if we use enriched uranium, then we will require only 30 tons of uranium in a year. Now, let me tell you what is enriched uranium. See, first I use the term natural uranium. So let us see what is natural uranium. Natural uranium basically, essentially consists of 2 isotopes of uranium, though there are some other things, but let us not talk. Majority of it is uranium-235 and uranium-238. Now, uranium-235 is only about 0.7%. Okay, while the rest, 99.3%, is uranium-238. So the bulk material is uranium-238, while the minor material is uranium-235. But when we want to run a reactor, we essentially need uranium-235. Okay, so if we are using natural uranium as the fuel, the amount of fuel present in the uranium is little less. It is only 0.7%. Okay, so the volume of the reactor will be relatively larger. See, for example, if you are putting 100 gram of uranium, essentially only 0.3 gram you will be using. Rest 99.7 gram will not be generating electricity. It will give you something else, but it will not generate electricity. Okay, so that is why you require more amount of uranium. But if you increase the concentration of uranium-235, let us say about 3 to 5%, 3, 4, 5% from 0.7%. So then what will happen? No more uranium is available. I mean, more fissile material is available. So more electricity will be generated. And that is why for the same size of nuclear reactor, the requirement of the fuel will go down from 160 tons. You require only 30 tons, because in 30 tons itself, you will get those many fissile atoms. So how do you increase the concentration of uranium-235? What do you do? So I will give you an example from kitchen. So you have milk. Every day you take milk. Okay. So what is milk? What is the bulk material in the milk? I think all of you know bulk material in milk is water. Okay. Only very small quantities of the components because of which it is known as milk. So the milk component is essentially very, very small. So now your mother or in the market, they convert milk into a thicker milk. Okay. It is in the what is available in the market in packed dabba, it is known as condensed milk. Okay. I think your mothers will know it very well if you do not know. Condensed milk. Okay. If your mother needs to make this gulab jamun in the house, she will need this milk made, or she wants to make kaju barfi in the house, or many other preparations, nariyal barfi, etc. in the house. She will need milk made, that condensed milk. She will be using that. So that is essentially enriched milk. What has been done in preparing that? Bulk of the material, water, has been removed by evaporation. Okay. By evaporation, that water has been removed. So concentration of milk has increased in that. Same thing is done in case of uranium. So what we are calling as enriched uranium, you can, I mean, for the sake of understanding, you can call it condensed uranium, just like you call condensed milk. Okay. So how it is done? There are various methods of doing that. I mean, you don't evaporate. I mean, naturally, uranium is not a liquid, so you don't evaporate, you don't vaporize uranium-238, but there are some methods of doing that. You separate them by gravity or by thermal diffusion, by chemical diffusion, and there are some other technologies. Let us not go into that. So that is what is meant by enriched uranium. Okay, so you will need only 30 tons of enriched uranium for running a 1,000 megawatt electricity plant, nuclear power plant, for a year. And the same plant, if you were to burn coal, then you will need about 38 lakh tons of coal in a year. So please compare 160 tons or 30 tons with 38 lakh tons. And please remember that this 38 lakh tons, majority of the material present is carbon. So when it burns, it produces carbon monoxide and carbon dioxide. And you know the problem with carbon dioxide. The world is struggling today with global warming. Okay, so we want to reduce the concentration of carbon dioxide in the atmosphere. So essentially, if you are burning so much of carbon, so much of coal in a year, naturally you are increasing the problem of global warming. Okay, and in addition to that, it has so many impurities. For example, it has sulfur. So when carbon burns, the sulfur component also burns, and it produces sulfur dioxide, sulfur trioxide. So that causes pollution. Then again, when the carbon is burning, and naturally you need air for the combustion to help in combustion. So nitrogen is also available along with oxygen. So that nitrogen also at high temperature combines with oxygen. So nitrogen starts consuming some of the oxygen, and nitrogen oxides are produced, which are again pollutants. So thus burning of the coal produces global warming gases and also the polluting gases. So that is why that is one advantage of using uranium. Let us go to the next slide, please. Now, when I say nuclear power plant, essentially what do I mean? So just to give you a very, very simple comparison, I have depicted the schematic of a thermal power plant and a nuclear power plant. Okay, so in thermal power plant, as you see on the left hand side, there is a furnace. In that furnace, the coal is burning. So coal is being continuously supplied. Coal is undergoing combustion. So a lot of heat is generated. And from the bottom, that cold water is entering. Cold means normal temperature, atmospheric temperature water is entering, and it is getting boiled because of the heat, and steam is generated. It is collected at the top, and in red color, red line, it is shown that steam is brought out from this furnace, and this steam is sent to a turbine. High pressure steam is sent to a turbine to rotate the turbine, and turbine is attached to a dynamo, and the dynamo generates electricity. As simple as that. Nuclear power plant also is as simple as that. Only thing is, you replace a coal-fired furnace by a nuclear reactor. So now no coal is burning. Instead of burning of coal, there is a nuclear reactor as shown inside with those red vertical lines. Those denote the nuclear fuel. So all the uranium is stacked there. When it undergoes fission, it produces enormous amount of energy in the form of heat. That heat has to be transported. So just like in case of coal, a cold water goes into the nuclear reactor and the hot water comes out. But here, the this water is in a closed circuit. As you can see, it is in a closed circuit because we do not want the water which is going into the nuclear reactor to come out in the public domain. See, after all, it will contain some radioactivity. And by chance, normally it will not happen, but by chance, if there is a small leakage, etc., then radioactivity will come into this water. And this water, if you are taking out of the reactor building, it will go to the turbine. So the turbine hall will become radioactive, and the entire place will become radioactive. So to confine the radioactivity within the reactor building, to avoid spread of radioactivity, we follow the concept of primary coolant. So as you can see, there is a primary coolant inside. The cold, it is shown, the two lines are shown in maroon color. One line is entering the reactor. So it collects the heat, becomes heated up. Okay, it goes to a heat exchanger. Okay, in the heat exchanger, as you know, I think, otherwise I will explain to you. In a heat exchanger, always there is a tube side and a shell side. Tube side contains the liquid from which you want to transfer the heat. You want to remove the heat. Okay, and the shell side will contain the liquid to which you are transferring the liquid. To give you a popular example, if I was physically present with you and if I had asked you the question, how many of you have seen a heat exchanger in your life? Probably your answer, maybe except one or two people, your answer would have been you have not seen a heat exchanger in your life. But actually, I can tell you, all of you have seen a heat exchanger in your life. The example is once again from your kitchen. Okay, so morning when your mother boils the milk. Okay, again I'm coming back to milk. Very fond of milk. Okay, so your mother boils the milk for you. You are getting late for the school or college, wherever you go. Your bus is about to come, but milk is too hot for you to consume. What does your mother do? She does some magic. She brings down the temperature of the milk. How does she do it? She takes the milk in a small vessel, preferably made of aluminum. In that she puts the milk, and that milk she puts in a larger vessel filled with water, tap water, and she does some magic. She rotates that vessel, and look, within 2, 3, 4 minutes, the milk temperature comes down. And if you dip your finger in that larger vessel, that water would have become little hotter because heat has transferred from smaller vessel to the larger vessel. So see, this is what is the most primitive the mother's heat exchanger. So the principle is the same, that in the tube side, so as you can see on the top, that zigzag line is going. That is the heat exchanger, the tube side of the heat exchanger. It is surrounded, that another vessel around it. It is filled with the normal water. Okay, so the first circuit is known as primary coolant. Okay, and this circuit is known as primary heat circuit. Okay, so all the heat it will deposit uh, in the heat exchanger, and the water there will get boiled. And once again, just like in case of coal plant, that steam will be brought out and it will be used to rotate the turbine. And to replenish the water in that heat exchanger shell side, the cold water, just like in case of coal plant, it was going. The cold water will be entering into that vessel. So here you have a primary coolant, you have a secondary coolant. So primary coolant circulates within the nuclear reactor, okay, and the secondary coolant is the one which brings the heat out from the nuclear reactor and gives it to the turbine. We have certain reactors, I'll be talking after a little while about them, where you have even a tertiary coolant. So you have a primary coolant, you have a secondary coolant, and then ultimately you have a tertiary coolant, which essentially brings the heat out of the nuclear reactor. I'll explain about it when we come to that. So right now, I think probably you have understood that how a nuclear reactor uh, uh, converts the energy released by nuclear fission into electricity. Okay, let's go to the next slide and talk a little more about nuclear reactor. So essentially, as all of you know, I mean, I have told you that nuclear reactor is the device that conducts the controlled chain reaction, controlled nuclear fission. So I think when we were discussing fission, there was a diagram, I think I forgot to mention about it. So you know what is a chain reaction. So see, I had told in every fission, 2 or 3 neutrons come out. What will these 2 or 3 neutrons do? They will go and irradiate, they will bombard other nucleus. That nucleus will undergo fission. So let us say first fission occurs, 3 neutrons come out, these 3 neutrons hit another nucleus. So now 9 neutrons will come out. Okay, and in one fission, 200 million electron volt had come out. Now 3 fissions have taken place. So 3 into 200. So 600 million electron volt energy will come out. Now from 3 fissions, 9 neutrons will be produced. Those 9 neutrons will hit another 9 nuclei. Okay, so now 1,800 million electron volt of energy will come out, and 27 neutrons will be produced, and the process will go on. I am taking too much of time in saying so. Actually, this will happen. The entire mass of uranium present there in that device will explode. It will undergo fission within a fraction of a second. So that is what is known as uncontrolled chain reaction. Okay, so in a reactor, what we do? We control the chain reaction. How do we control it? I will tell you. Okay, so every time see, it is not done at a micro level. So what essentially you have to do, every time a fission is taking place, 3 neutrons are coming out, absorb 2 of them. I mean, remove 2 of them. So only 1 will be left. That 1 will go and hit another nucleus. So again 3 neutrons will be produced. So again absorb those 2 neutrons from that. So only 1 will be allowed to go. Okay, so like that, one by what you are doing, you are making the uranium atoms to undergo fission one by one, slowly in a steady state manner. Okay, so essentially you get time to transfer. Every fission will be producing the 200 million electron volt of energy. You are getting sufficient time to remove it from the nuclear reactor and convert it into electricity. So that means you need a material which can remove neutrons. Okay, so some such material, that means you require neutron absorbing material. Some such materials are boron, cadmium, hafnium, gadolinium. These are the materials which absorb neutrons. So I think I'll be coming to that when I talk about control rods. So I thought here itself I will tell you. So these things like boron, cadmium, etc., they are used to absorb the excess neutrons. So it is done at a macro level. See, you can't go in a microscopic manner and see that, okay, one fission has occurred, so capture the two neutrons. You can't really do that. So it is done on a statistical level, at a macro level, that you introduce control rods made of boron and you position them, their number and their position is such that on an average, you will be removing 2/3 of the neutrons produced, so that only 1/3 will be allowed to go ahead. But this also is adjusted. So essentially, this is what is a nuclear reactor. Now, what does it do? What does a nuclear reactor do? It produces power. Essentially, it produces heat. Okay. So that heat is converted into electricity. Then what else it does? It converts fertile material to fissile material. See, I told you the nuclear fuel you will be loading here will be a mixture of uranium-235 and uranium-238. Okay, so uranium-235 will undergo fission and give you electricity. But what will happen to uranium-238? I have already told you. It will absorb the neutrons and will get converted into plutonium-239. Okay, so that means a nuclear reactor converts fertile materials to fissile materials. So that you can use that fissile material as nuclear fuel in some other kind of nuclear reactor. And the third thing, what it does, it produces radioisotopes. How does it do so? Because it is a rich source of neutrons. So if you put any material in the nuclear reactor, that material will absorb neutron and will produce a radioisotope. Okay, and that radioisotope will have some application. So please remember, a nuclear reactor essentially does three things. It produces heat from which electricity can be generated. It converts fertile material into fissile material, and it produces radioisotopes. Now, what are the components of a nuclear reactor? Naturally, first thing is you need a fuel. So fuel is a mixture of the fissile and fertile materials. For example, I told you the simplest thing is the mixture of uranium-235 and uranium-238. It's a mixture provided by the nature. Okay. Then second thing is moderator. See, please remember one thing. What is it? See, first let me tell you what is moderator. So as I told you, the neutrons which come out during fission, you have plenty of energy. That essentially 200 million electron volt is there. So much of this energy will be carried by these neutrons. So these neutrons will be moving at a very high speed because of this high energy available with them. So they are known as fast neutrons. Fast neutrons means because they are fast moving neutrons. On what basis you call them fast? Because they are moving at a speed much faster than in a gas, the gas molecules are moving, you know, so they follow gas equation. PV is equal to nRT. Okay, they follow. I mean, in a gas, when a vessel is filled up of gas, you know, it follows the gas equation. PV is equal to nRT. So there, that the energy of the particles, gas particles, is much, much less as compared to these neutrons. So that is why these neutrons are known as fast neutrons. But unfortunately, these fast neutrons, they are not good for causing fission in uranium-235. You need slow neutrons. You need neutrons whose energy can be compared to that gas particles, you know. So that means you need to reduce the energy. So it has been seen that the probability of fission of uranium-235, it increases, you know, it is proportional to or inversely proportional to the square root of energy of the neutron. So if you decrease the energy of the neutron 10,000 times, the probability of fission will go up by 100 times. Okay, as I told you, probability is proportional to 1 by square root of the energy of the neutron. Okay, so how do you reduce the energy? It's a fast moving particle. You want to reduce its energy. So again, you go to fundamental physics. Okay, elastic collision between bodies. I think you must have studied in your physics. Okay, so elastic collision between fast moving bodies, and you must have seen on the billiard board also, that is what it happens. One particle is stationary, so you strike a ball, that ball is having kinetic energy. When it hits another ball, it loses kinetic energy, the other one gains. So same principle is used here. So naturally, if you study that elastic collision, so two bodies of mass m1 and m2, I think definitely you must have studied already. So the transfer of energy from one body to another body is maximum in per collision if m1 is equal to m2. So if the mass of the two bodies is similar, comparable, or equal, then the transfer of energy will be maximum per collision. So that means for neutron, the best moderator will be neutron itself. But now it is difficult to, impossible to get neutron as a fluid. So how can I supply neutrons? So what is the next best? Next best is proton. Okay, proton, because its mass is almost equal to neutron. So proton will be a very good moderator. That means proton means H2O. In H2O, there are two protons, H2O. So two hydrogen atoms are essentially protons. Okay, so that means water will be a very good moderator. But now there is another problem with water. If you are using natural uranium as fuel and you use water as a moderator, then water is not very honest, or this protium H is not very honest. It is given the job of reducing the energy of neutrons, but it starts eating some of the neutrons, because this protium H has a very good cross section for absorbing neutrons. So this H starts absorbing neutrons. So that means your number of neutrons will decrease. So that is why if you are using natural uranium as fuel, then you are not suggested to use ordinary water as a coolant moderator. And that is why we go to, so what is the next best? The isotope of hydrogen, deuterium. So if instead of H2O, if you use D2O, you can use that as moderator. So generally, when we use uh, natural uranium as fuel, we use heavy water, D2O, as the moderator. And for the same reason, we use D2O as a coolant also. Because again, if you are using ordinary water as a coolant, it will start absorbing neutrons. So your neutron economy will be disturbed. So that is why when you use natural uranium, you use heavy water as a moderator and coolant. And essentially for that reason, such reactors are known as PHWRs, pressurized heavy water reactors, on which in fact India, Canada, these are two basic countries who have a lot of reactors of this type. Okay, so now let us, so I told you about the moderator. Okay, then other possible moderators, in some reactors, they have used graphite also as a moderator. The Chernobyl reactor, which had undergone accident, which exploded, that had used graphite as a moderator. And essentially that was the problem. Actually, once the reactor exploded, at high temperature, graphite started burning, because tons of graphite was there in that reactor. So the graphite caught the fire because of high temperature, and anyway air was available, so it was burning, the graphite was burning. So that is how the Chernobyl accident happened. So in India we have never used graphite as a moderator, but some people have used it. Now we come to control rods. I have already told you what is the purpose of the control rods, to control the number of neutrons. So statistically it removes, so you make rods made of boron carbide. Okay, so that boron, if you lower that control rod into the reactor, more neutrons will be absorbed. But if you remove the control rod from the reactor, then number of neutrons will increase, so the power of the reactor will increase. So that is how the power of the nuclear reactor is controlled, by using these control rods. Okay. Then last but not the least, very important thing is the coolant. So coolant is a fluid circulating through the core so as to transfer the heat from it uh, uh, essentially to the turbine room. Okay, that heat has to go from here and has to reach the turbine room so that heat can be converted into electricity. Of course, heat is not directly getting converted into electricity. Heat first becomes the potential energy of the steam, and that potential energy is converted into kinetic energy of the turbine, and in the dynamo that kinetic energy is finally converted into electricity. Okay, so much so about nuclear reactors. Let us go to the next slide. So in India, particularly in India, we follow a 3-stage nuclear power program, and now I will recall that I had shown you where I had introduced you to the 3 fissile materials. First one was natural fissile material, uranium-235, and then next one was plutonium-239, which is obtained by neutron bombardment of uranium-238. Okay, and the third fissile material was uranium-233, which is made by neutron bombardment of thorium. Okay, so please recall that those 3 fissile materials. So now 3 stages you see vertically. This slide can be divided into 3 portions. So the first column is the first stage, middle column is the second stage, and the third column is the third stage. Of course, it is depicted also. It is written there. Stage 1, stage 2, stage 3. So stage 1, essentially, there is fission of uranium-235. So naturally, the fuel used is either natural uranium or enriched uranium. So if you use natural uranium, your reactor type will be PHWR, pressurized heavy water reactor. Okay, that means you will be using heavy water as the coolant and moderator. So India has majority of its reactor of this type. Second possibility is light water reactor. Light water reactor means your fuel becomes enriched uranium and your moderator and coolant is ordinary water, means light water. We call it light water. Okay. So this light water, here you can use light water as a moderator and coolant because your uranium is now enriched. It contains more fissile material, so there will be large number of neutrons. So neutron economy is not too much. I mean, there is no problem. You can waste some of the neutrons. So that is why here you can afford to use ordinary water called as light water as the moderator and coolant. So in fact, in the world, about 60% of the reactors are of light water type. I mean, majority of the reactors are of light water type in the whole world. But it was only Canada was the first country to develop PHWR technology. Then with their help, we made 1 reactor. We were supposed to make 2 reactors with their help, but after making 1 reactor, they went away. They suspended the collaboration with India. And so the second reactor we completed, and in the process, we learned how to make those reactors. And after that, now we have, in fact, improved upon the designs, and we have our own Indian design of PHWRs. So 18 of them are operating, 6 of them are under construction, and many more are planned. They are in the pipeline. Okay. And light water reactors again can be of 2 types. So one is boiling water reactor, and second is pressurized water reactor. So, um, uh, so light water reactors, further two categories. So as the names themselves are suggesting, boiling water reactor, where the primary coolant itself boils. You know, the water which is, and there is no separate moderator. Here, the same water acts as a moderator also and as a coolant also. Although in your PHWR, though the material is same, heavy water, but the coolant liquid is different and the moderator is different. I mean, they are in different pipelines. They are in different vessels. Okay. So now here, it is just like, you know, boiling water reactor, it is something like immersion heater. See, I mean, sometimes if your geyser is not working or something, a very cheap device is available in the market, suspension heater. So you bring a suspension coil, it is called. So people who do not have a geyser in their houses, particularly in winter season, they will bring these suspension heaters. They will be suspended into a bucket and put on. So the bucket water will start becoming hot. Okay. And ultimately the water will start boiling. So this boiling water reactor is a device of that kind. So instead of the suspended heater, there is a nuclear reactor hanging into the vessel and it is full of water. That water boils and that steam is used to rotate the turbine. So those are called as boiling water reactors. But then there are certain disadvantages in them. So we go to pressurized water reactor. Now in pressurized water reactor and also in pressurized heavy water reactor, what is done is that this coolant is at high pressure. Now I think all of you know, I think by 10th standard you are taught what is elevation of boiling point. Okay, so the pressure of a liquid, its boiling point elevates, it increases. And in fact, that is the working principle of a pressure cooker. Okay, normally water will boil at 100 degrees centigrade. So if you are doing a conventional cooking in an open vessel, your vegetable or your dal or whatever is the food is being cooked at 100 degrees centigrade. Okay, because water boils at 100 degrees centigrade. So sometimes it will take more time, you know, at lesser temperature, more time will be required for the food to get cooked. So instead, somebody designed a pressure cooker in which the steam is not allowed to go out. In a pressure vessel, in an open vessel, steam is getting lost. So that is why the temperature is only at 100 degrees centigrade. But in a pressure cooker, you don't allow steam to escape. So pressure increases. Because of pressure, the temperature of the liquid increases. So the food, if you have increased the pressure in the pressure vessel, in that cooker, so instead of 100 degrees centigrade, now the water may be boiling at 110 degrees centigrade. So now your cooking is happening at 110 degrees centigrade, and that is why the cooking happens very fast. Okay, this is essentially the principle of working of a pressure cooker. Same principle we have used. Of course, here the pressure is increased very, very high. I mean, to the order of 300 psi, etc. And at this high pressure, the water temperature, boiling point goes up to 300 degrees. Instead of 100 degrees centigrade, it goes beyond 300 degrees centigrade. So pressurized water. So we have increased the pressure so it doesn't boil. It goes as a superheated liquid. So the primary coolant does not boil. It remains as pressurized liquid. That pressurized liquid, when it goes to that heat exchanger, which I had told you, in the heat exchanger, it will give away the heat to another water, which is coming from outside. That water is at normal atmospheric pressure. So because of this enormous amount of heat, that water will immediately boil. Steam will be produced. So in PWR and in PHWR, please remember that the coolant is at high pressure. Okay, so it does not boil. So this is what is first stage. So we are already having 18 reactors operating PHWR type under construction 6. Then we are having light water reactors, 4 are operating, 2 are boiling water reactors, and 2 are pressurized water reactors. And actually 4 more are under construction. This presentation I had sent to your spot team somewhere in October. Now situation has changed a little, so 2 more reactors are under construction. So instead of under construction 2, it should be under construction 4. Okay, so now then comes the second stage. So in the first stage, uranium-238 is getting converted into plutonium-239. So the spent fuel, the fuel which has been used up in the nuclear reactor, that used up fuel is known as a spent fuel. When it is taken out and fresh fuel is put into the reactor, so this spent fuel, it will consist of what? There will be some unused uranium-235 because all of it must not have undergone fission. Okay, then there will be some unconverted uranium-238 which could not be converted into plutonium. Okay, and then there will be some plutonium, which that uranium-238 which got converted into plutonium, that plutonium will be there. And then whatever uranium-235 underwent fission, those fission products will be there, the products of fission. So this is what will be there in that spent fuel. So this spent fuel is taken out. It is cooled for some time because it is generating a lot of heat. There is a lot of radioactivity inside. So it is cooled down in a tank of water. And after it has sufficiently cooled down, it is sent to what is known as reprocessing plant. There, this spent fuel is cut into pieces, all remotely because it is highly radioactive. So nobody does it in, I mean, I'm showing an action as if somebody is cutting it with a hacksaw blade. No, nothing of that sort. Everything happens in hot cells. No human beings are present. Okay, so it will be cut into small pieces, dissolved in acids, and then some chemistry will be done on it, and plutonium will be separated, uranium-238 will come out separately, U-235 will come out separately, and fission products will go out separately. That chemistry is done on that. These plants are known as reprocessing plants. So now whatever plutonium-239 you have recovered, that you mix with uranium-238, which is the fuel for the second stage. In the second stage, you are using a mixture of uranium-238 and plutonium-239 as the fuel. 30% is plutonium-239, 70% is uranium-238. Okay, now your fissile material has changed. It is not uranium-235, it is plutonium-239. And the nuclear property of plutonium-239 is different from that of uranium-235. Here, you can, fission probability is good with fast neutrons also. So essentially, a difference between the first stage reactor and second stage reactor is that in the second stage reactor, we don't need a moderator. So no moderator is required. So since no moderator is required, that means you are using fast neutrons directly. So that is why these reactors are called as fast reactors. Okay. Now, in addition to that, you have loaded them with uranium-238. Now that uranium-238, because plenty of neutrons here are available, because in these reactors, 30% fissile material is there. Remember, we have loaded 30% fissile material. So lot of fissile material is available. With the result of that, lot of neutrons are available. So these neutrons, naturally, they will convert more uranium-238 into plutonium-239. So that plutonium-239, so that means there is a breeding taking place. You know, it is just like a poultry farm. There are hens, there are eggs. The poultry owner is selling the eggs, he is selling the hens, but still the number of eggs and number of hens is going on increasing. How it is happening? Because breeding is taking place. Some of the hens are giving the eggs, some of the eggs are sold, but some eggs are hatched those eggs are giving birth to new hens. Those hens in future give more eggs. So this goes on. And this is how through the breeding, the inventory is maintained. In fact, the inventory is increasing in a poultry farm. If the poultry farm is doing a good business, its sales will increase and its inventory also will increase. Okay. So we have borrowed this term from there, that we breed nuclear fuel. So we loaded 30% uranium-238. So that uranium-238, 30% plutonium-239 we loaded, that will give us the electricity. That will give us the energy which will be converted into electricity. So in a day, let us say certain number of these plutonium nuclei will undergo fission. So they are over. That means they are the eggs which have been sold out. They have been spent. They are no more available in the poultry farm. So our hens are uranium-238. So the uranium-238 will give birth to new plutonium nuclides. And so we design the reactor in such a way that the amount of plutonium produced should be higher than the plutonium which is being used. So number of eggs produced should be more than the number of eggs which are getting sold out. That is how a poultry farm becomes successful. So same way, this second type of reactor, this reactor of the second stage, it is designed in such a way that the breeding ratio is more than 1. That means the amount of plutonium you are consuming, more than that you are producing. And so that means you are breeding the fissile material. That is why we call this reactor as a breeder reactor. That is why the total name of this type of reactors is fast breeder reactor, FBR. So this is what is meant by fast breeder reactor. Okay. Now, so what is the status of India? In fact, India is in a leading position in fast breeder reactor technology. There are not many countries who have mastered this technology. France, Russia, USA had done, but now presently you see Russia is not doing much in this field. And then Japan was there in this field, and India is there. So way back in 1985, we had put up a fast breeder test reactor, which was a 40 megawatt thermal, and it is producing electricity also, but about 12 megawatt, 13 megawatt electricity it is producing. It's known as test reactor. So it is, and it had, a specially designed novel fuel. It was a mixed carbide of uranium. Let's not get into that. But just for your knowledge sake, I'm telling you, it was a novel fuel, first time used in India, a mixed carbide of uranium and plutonium. Okay. And it has been operating since then. Its objectives have been reached, but still we are operating. And based on the experience gained with this fast breeder test reactor, we have constructed a prototype fast breeder reactor of 500 megawatt electric. So from 12 megawatt electric, we have directly gone to 500 megawatt electric. So this has actually, the construction is over. It should have started, but they are doing certain investigations because it is first of its kind reactor. Not much of world experience is also available. So we are being very, very careful, and our Atomic Energy Regulatory Board, who look after the safety involved in these nuclear reactors, so they are not allowing us to start the reactor. They want us to solve certain problems in that new type of reactor. So it is taking time. Otherwise, the reactor is ready. Then we come to the third stage. The third stage, as now you know, I think the third fissile material is left, uranium-233. So the third stage will comprise of the fuel based on uranium-233. So again, this is a special thing. I think India is in a leading position in this as far as the third stage is concerned. But the question is that thorium. So thorium, which is found in very large quantities in India. Uranium, we don't have much in India, but thorium, we are having large quantities. So this thorium, but unfortunately, you can't start a nuclear reactor with thorium because it does not contain any fissile material. So that means in a running reactor, you have to convert thorium into uranium-233. So you can do that in any type of reactor, but in PHWR, our PHWR reactors, as I already told you, we don't have much neutrons. So we can't convert the thorium there. So majorly, thorium is being converted into uranium-233 in the fast breeder reactors. As I already told you, we have plenty of neutrons there. So we are really not bothered about the, economy of neutrons. So what we do around the nuclear fuel, we put rods of thorium also, and we call them as blanketing. So the fuel is blanketed by thorium. So I mean, it's a term used in nuclear technology, that blanketing the fuel with thorium rods, so that neutrons will come and convert thorium into uranium-233. Okay, so you will have two materials for reprocessing here. One, the fuel, which will be used in fast breeder reactor. So naturally, whenever you take out the fuel, it will contain some unused plutonium, it will contain some unused, unconverted uranium-238. So that reprocessing will be done separately, plus the blanket material that you will take out, and it will contain some unconverted thorium, and it will also contain some uranium-233. So that separation also is done in another reprocessing plant. And then this, you get uranium-233, and anyway you are having thorium, so you make fuel for the third stage. And in the third stage, your fissile material is going to be uranium-233. There is no operating reactor anywhere in the world on this using uranium-233, and India is in the leading position, and we are designing and doing a lot of R&D on various kinds of reactors. Some of them are advanced heavy water reactor, then molten salt breeder reactor, then high temperature reactor, and accelerator driven subcritical systems. I think these are beyond the scope of today's talk, so I will not be talking about them. But I want to very proudly, I want to tell you that in 90s itself, we had put up this Kamini reactor. You see at the bottom in the third column, that picture, Kamini. It means Kalpakam mini reactor. I mean, it's not the name of a girl. It is Kalpakam mini reactor. Okay. So this was put up in 90s, and it is still operating. So essentially, actually, Kalpakam in Tamil Nadu is a special place for nuclear industry and very proud place for India. It is the only place in the entire world where fission of all the three fissile materials is going on, because we have two reactors there, Madras Atomic Power Plant. Those are using, they are causing fission of uranium-235. We have FBTR, and the PFBR is also coming up there only. So there, the fission of plutonium-239 is going on, and we have Kamini research reactor there, where the fission of uranium-233 is happening. So the only place in the world, Kalpakam, where all the three fissile materials are undergoing fission. I think I'm losing time. Oh my God. Up to what time I can go?
So actually, we crossed the time limit.
We have passed the time limit.
Yes, sir.
Okay, so maybe today I was more elaborate or slow. So shall I restrict myself to electricity program only today? It's up to you. You have to decide.
Sure, sir.
So I should restrict to nuclear power program. This first
Yes,
topic.
yes, yes.
Radio isotopes, etc. You can call me anytime. If these children are available, I can complete another time.
Thank
There is
you
no
so
problem.
much.
I am available. I am a retired fellow. So I am available. In fact, my favorite hobby nowadays is delivering lectures. So I can deliver. So, okay, I think I will finish with this nuclear power program. And if the children are interested, sometime in future, we will have this radioisotopes and their uses. Okay. So
yes,
let me complete the nuclear power program. I think another 2-3 slides are there.
Sir, all the students are requesting you to continue. They're thoroughly enjoying the session because all the messages in the chat box are saying to please continue.
I have no problem. I can continue. See, you told time is over, so that's why I told.
Yes, sir, because we have the question and answer session as well.
If I complete, it will go. I mean, it can go beyond, much beyond 6:30.
All right, sir. I think then we'll have to keep it for another day then, because we
So
have to
you
take
can
in
tell the
questions.
students as per their convenience. I am available. See, I don't require any formality that you are having a program. I mean, these are webinars, so you don't have to even arrange a stadium or anything.
Yes,
whenever
sir.
these children are available, I am always available. So if you arrange a program, I will complete. So now you decide accordingly. Let me.
Yes, sir, you can go ahead with this topic, sir, and finish it off, and then we'll start with the question and answer session.
Okay. So let me finish off this nuclear, the electricity program. Okay. So children, I think I have already told you about these 3 stages. Now let me come and tell you that what is the status of our nuclear power program. So Indian nuclear power plants, in the center column, anyway, you see pictures of a lot of them. On the left hand side, a table is given. This is the table of operating nuclear power stations in India. So first one, in yellow color, you see there are 4. Tarapur 1, 2, 3, and 4. Tarapur is located in Maharashtra. It is about 120 kilometers from Mumbai. Okay. So let me tell you about TAPS 1 and 2. They are the oldest nuclear power plants of India. They are boiling water reactors. Both of them are boiling water reactors. They were put up in 1969. Actually, they started generating electricity. That date I can never forget, because they started generating electricity from 2nd October, Mahatma Gandhi's birthday, 1969. Okay. So they are boiling water reactors. Okay. I already told you what are boiling water reactors. These reactors are similar to the reactors of Fukushima, which underwent that. I am clearly telling you, they are of that vintage and that technology only. But in India, we have modified the design. So here, that Fukushima type of thing happening is ruled out. Okay. We have taken, already in the design, there were certain aspects like that what happened at Fukushima will not happen here. But in addition to that, after the Fukushima accident, we did a thorough study, and we have made them very strong. Already, as you know, they are now about 50 years old. In fact, more than 50 years old. In 2019, they became 50. So we have extended their life. So I think another 10 to 20 years they will be running. And we are very sure that they will run in a very safe manner. Then the TAPS 3 and 4 are our largest PHWRs amongst the operating reactors. They are 540 megawatt pressurized heavy water reactors. They were made somewhere in 2005. So they are operating since 2005. Okay. Then we have Rajasthan 1, 2, 3, 4, 5, 6. So 6 reactors are operating. They are operating at Rawat Bhata near Kota in Rajasthan. So the first 2 reactors, RAPS 1 and 2, they are of the Canadian design. Okay. So original Canadian design, both of them were supposed to be 235 megawatt, because the design of Canada was 235 megawatt. So they started building, and the first reactor actually somewhere around 1972, if I remember correctly. Yeah. 1972, the first reactor started operating. And then second one was under construction, and it was it should have become operational somewhere in 75, 76. But in 1974, India conducted an underground peaceful nuclear experiment in Rajasthan only, because of which Canada became very unhappy with us. It suspended all nuclear cooperation with us, so that second reactor uncompleted, they left it and they went away. They went back to their country. And so our engineers and scientists completed this reactor, and but it took some time because naturally we were new. So it took some time for us, but by 1981, we started this reactor also, RAPS 2. But in the process, we became very smart. We could now design our own PHWRs and make them. So after that, of course, the rest of the PHWRs we have only made, and we standardized the design of 220. Now Rajasthan 1, you see that it is 100 and Rajasthan 2 is 200. Their power has been decreased. Of course, Rajasthan 1 is now actually closed down. It is not even 100. It is permanently closed down because it has some safety issues. So it has been closed down. Rajasthan 2 is operating at 200 megawatt, and the rest of our power stations are all 220 megawatt. So we had standardized 220 megawatt. This is our own design. So you have 4 of them operating in Rajasthan in addition to the Canadian ones. Then Madras 1, 2, that is in Tamil Nadu, Kalpakkam. Then Narora Atomic Power Station 1 and 2 in Uttar Pradesh near Bulandshahr. Then Kakrapar Atomic Power Station 1 and 2 in Gujarat near Surat. Then Kaiga 1, 2, 3, 4. They are in Karnataka. And then, of course, we have with the Russians collaboration, we have made this KKNPP, Kudankulam Nuclear Power Plant 1 and 2, which started in 2013 and 2016. And so they are operating. Now let us come to the under construction reactors. So under construction, there is KKNP 3 and 4. And in fact, again, this slide being slightly old, few months old, there is now KKNPP 5 and 6 also. So 4 KKNPP type of reactors are under construction. And then we have prototype fast breeder reactor, which I already told you is almost ready, but undergoing certain studies and investigations. Then we have Kakrapar Atomic Power Station 3 and 4. So Kakrapar 1 and 2 is already there, 3 and 4 is there. And these are now, we have gone for a larger PHWR design, 700 megawatt. So 2 reactors of 1400 megawatt. And then similarly, Rajasthan 7 and 8, up to 6 they are operating. So 7 and 8. And then there are 2 more actually. Again, there is no mention of them. In Haryana, there is a small place called Gorakhpur. There is a larger Gorakhpur in Uttar Pradesh, but there is a small Gorakhpur in Haryana. So there it is there. Gorakhpur Anu Vidyut Pariyojana, it is known as. It was launched in 2020, and it is under construction. So these 2 reactors, you can add another 2 reactors. So that means presently we have 22 operating reactors with total installed capacity 6,780 megawatt. Under construction is 9 reactors. Actually, it should be 8,700 because those 2 reactors, KKNPP 5 and 6 has to be added. So it is 8,700 and then approved by government. Now this 12 reactors should become 10 reactors because 2 of these have gone into construction. Okay. So now 10 reactors with 7,000 megawatt. They are approved by the government, but construction we have to start. So now I think children, today I will restrict here because of the paucity of time. I have no problem. Okay, I could have gone up to 8 o'clock also, but I think they are right. So let us break these lectures into 2. Maybe any other time, whenever you are interested and the spot team, the organizing team is ready, is in a position to conduct. Any time, any day, I am available, including Sundays. So with that, I thank all of you. So next time, whenever we meet, if there is a chance to meet, we will start from here, radioisotopes. Okay. Thank you very much.
Thank you so much, sir, and for offering to have another session when we do have the time to plan another one. We'll move on to our question and answer session. Maybe you will get more insights to all our students when sir answers your questions. When we move on to the questions, I will call out your names. I've picked up a couple of questions from the chat box. Kindly ensure that you unmute your mic. I will be requesting you to unmute your mic. Introduce yourself with your name and your class and your school. All right, our first question is from Akshit Lal. Akshit Lal, can you please unmute your mic?
Good evening, everyone. I am Akshit Kumar Lal. I have a question that is nuclear fusion can be the future for truly green energy, because we have seen the power of nuclear fusion in the hydrogen bombs that we have. But when we consume the nuclear fusion energy, we do not get any nuclear waste. That is very advantageous for us. So can it be the clean energy?
Yes. Yes, Akshit, you are very right. In fact, fusion energy will be the future source of energy. In fact, earlier people were thinking that it will be, I mean, maybe around 50 years back, people thought that in 20 years from then. So that means by the year 2000, fusion energy should have come. But it was not so simple, because in fusion, the major problem is, see, when you do hydrogen bomb, that means you are doing uncontrolled fusion. So there is no problem. So to tame fusion so that it can be used to convert all that tremendous amount of energy into electricity. Let me first tell you that the amount of electricity per fusion is even much more than this fission. So that means much more energy is available. And as you very rightly said, there are no fission products there, because there you are taking lighter nuclei and you are combining them, you are fusing them together to become a heavier nuclei. So for example, deuterium and tritium, they fuse together and you will get helium. Okay. So like the fission products of fission, reaction will not be there. So that will be a very great advantage. But one of the great challenges has been in fusion that, see, there is a, when you grow up and study physics, you will come across a term known as Coulomb barrier. Qualitatively, I can tell you right now, two nuclei. So both the nuclei are positively charged. For fusing them, they will fuse only if they come close enough. Then only they will fuse. You know, I think in childhood, if you have, I don't suggest that you play with the mercury droplets. In my childhood, I got a chance to do so, because we used to have those conventional thermometers in the house. And whenever they will break, the mercury will spill. And using a piece of paper, we used to play with the mercury droplets. So there, what I used to observe, that these two drops of mercury, if I try to bring them close, then there used to be a time when they will attract each other and it will become one drop. Okay. So similarly, in fusion, it is like two nuclei have to be brought together, but there is Coulombic repulsion, because both are positively charged. Both the nuclei are positively charged. So there is a barrier created. They will not allow you to bring them together. So we say a barrier is created. So that barrier is known as Coulomb barrier. That has to be overcome. How do you overcome? Suppose there is a hill. On that you want the ball to go right up to the hill. So you have to give more and more kinetic energy from the bottom, so that it will be, or some vehicle has to reach the top of the hill. So you have to give a lot of acceleration right from the beginning so that it can reach the top. So similarly, we have to give a lot of energy to these particles so that they can fuse together. They have to overcome the Coulomb barrier. Now that energy is of the order of 10 to the power of 7, 10 to the power of 8 degrees centigrade or degree Kelvin. Actually, when you are talking 10 to the power of 7 and 10 to the power of 8, degree centigrade, degree Fahrenheit, and degree Kelvin doesn't matter. Be any degree, the temperature is 10 to the power of 7, 10 to the power of 8. Okay, that temperature. Now, at that temperature, matter can exist only in the plasma state. So that means your fuel, everything will be in plasma. Now it is a very difficult thing to contain plasma, and that too at higher pressure. See, we have plasma torches, so many plasma devices, but they are at sub-atmospheric pressure. The pressure is too less there. But if we want to make a nuclear power station out of fusion, we need to have a plasma at relatively higher pressures. So that is what is the challenge. So the whole world is busy in doing that. Individual countries are having their own programs. These devices are known as tokamaks. Reason being, I mean, first device was made in Japan, so they called it tokamaks. So this proper noun has come that any device you are making, it is known as tokamaks. So India also has its own 2 tokamaks. First one is Aditya. Both are in Gandhinagar in Gujarat. We have an institute called Institute for Plasma Research, IPR, which is located in Gandhinagar. So they built Aditya somewhere in 90s. And then second one is SST1, solid state tokamak. This SST1, which is more powerful than Aditya. So we are having our own program. Japan has their own program. Chinese have their own program. USA, UK, so many countries are having their own program. But I think by the year 2000, it was envisaged. It was understood that I think if we have to develop this technology fast, then a collaborative effort is needed. So there is a mega technology project known as ITER, ITER. It is located in France, but it has many partners. India is one of the partners. We are also participating, and a lot of money is required, but India doesn't give money. India is giving material. I mean, we are making things and supplying. Actually, I had a slide on this. So maybe next time when I talk, I'll be showing a slide. So yes, in future, fusion will be used as a source of electricity, and naturally it will be a green source of power. But only thing is we have to wait. Maybe I have lost hopes now. I am not left with many years in my life. I'm already approaching 70, so I don't think I will see an operating plant based on this, but definitely you guys are going to see it. All the best for that. Thank you.
Thank you, sir. We really hope you are able to live until we have the operating plant and you can talk to us and lead us through on it. All right. Yes. Akshay, thank you for your question. Our next question is from Rishabh Shah. Rishabh, can you please unmute your mic and pose your question?
Yes, I'm Rishabh Shah from grade 9th of the Kalyani school. My question is that why are typical cooling towers, why are they parabolic in shape? Why are they always curved inward? So could you just explain that?
Yeah, I will tell you. See, actually it has to do, see, down below where the steam is coming out. So it has to be, suddenly all the steam should not go out. So first it is tapering. That means the diameter is decreasing. Okay, diameter is decreasing with the height, so that all of a sudden all the steam is not lost, and then after some time you want it to diffuse into the atmosphere, and it should not gush out. So see, I think you can do this experiment in your house. A higher diameter pipe, when you decrease the diameter by pressing with your hand, pressure increases. Okay, So if you go on reducing the diameter, then at the top, the steam will be just gushing out at maybe at a little higher pressure. So when you want it to ultimately go into the atmosphere, you increase the diameter so that it slowly diffuses into the atmosphere. It's only that simple.
Thank you, Rishabh. Thank you, sir. Our next question is from Aditya Tripathi. Can you kindly unmute your mic? Aditya Tripathi.
Can you hear me?
Yes, you're audible. Please pose your
Yes.
question.
Yes, good evening to all. I'm Aditya from class 9, New Horizon Gurukul, Bengaluru. So my question was that what is your view on the antimatter research going on at the CERN in Europe? And has India looked into it? And is there any research going on in India about this?
Yes, in India also there are people working on antimatter, and of course it's high. I mean, it's high physics presently, and they say that actually the amount of antimatter is much more as compared to matter, which we see, that is matter. So amount of antimatter in the universe is much higher, and probably we do not know much about it. So yes, all around the world, at least wherever advanced physics studies are there, people are doing work on antimatter. In DAE, in our department itself, people are working on it.
Thank you, Aditya. Chinmayi, could you kindly unmute your mic and pose your question? Yes.
Good evening, sir. I am Chinmay. Yes, I'm studying in 9th standard from Atomic Energy Central School, Kaiga.
Oh, good. Nice to meet you.
My question was, sir, can you please provide some insights on the artificial sun that was developed by the Chinese? And also, I wanted to ask why production of energy by fusion is more difficult than fission.
I tell you, so that artificial sun is basically what I talked about. I think answering that another child's question, I told you that we increase the temperature to surpass the Coulomb barrier, and we create fusion. So when we create fusion, it emits large amount of energy, and as you know, everything is at that temperature, 10 to the power of 7, 10 to the power of 8. Okay, so at those temperatures, it will be shining bright white. So it will appear, in fact, it will appear, since we are seeing sun from a very, very large distance. So if we create a sun, I mean that kind of device here, so since we will be observing it from a very close distance, so it will appear brighter than the sun, though it will not be. So that is what is being, it is just notionally being called as an artificial sun. The idea is not to really make an artificial sun, but to make small devices where this fusion energy can be converted into electricity. And your second part is, I think I already answered. The basic problem is handling plasma at these high temperatures. So basically, it is not development of fusion technology. Fusion probably is well known, people can do it. But handling plasma at very high temperatures and confining it at higher pressures, so that to increase the throughput. Okay, that is what is the challenge. So the whole challenge is developing the technology, developing the plasma technology and sustaining the plasma for longer periods.
Thank you,
As I
Chinmayi.
told you, you will be seeing it in future.
Yes, sir. We really hope so too. Pradeep Kumar, can you kindly unmute your mic and pose the next question? Yes, Pradeep. We're unable to hear you. Pradeep, I know you've unmuted your mic, but we're unable to hear you. Okay, in the meantime, we'll move on to Dikshita. Dikshita, can you please unmute your mic and pose your question?
Good evening, ma'am. Am I audible?
Yes, yes, Dikshita, you're audible. Dikshita?
Yes, ma'am. Ma'am, actually, I was not able to unmute again. My question was, like, due to contamination due to radioactive waste which are produced due to nuclear reactors, um, how is it managed? Also, we consider ionizing radiation, which is actually a carcinogen. How are you guys able to manage those stuff? And further, if there's an accident, how are the people and the environment which are affected greatly for like hundreds of years, how do we cope up with that and how do we help them?
Oh, yes. Yeah. So let me start with this. I will give some very simple example. In the newspapers or in the news, you have heard more number of times about fire accidents or more number of times about nuclear accidents? Tell me frankly. Dikshita, you are supposed to answer my question also.
So majorly fire accidents actually.
Naturally. See, they happen more and they happen, right from industry to households. In every house, we have uh, these gas cylinders. And once in a while we hear, not really once in a while, if I think you keep a track of the country, I think every day so many cylinders must be bursting. One in Tamil Nadu, one in Uttar Pradesh, maybe one in Himachal Pradesh, like that. I think it is a everyday happening. Normally what we have done, we have learned to tame fire. Initially human beings must have seen fire, but later on they learned to tame it. So more or less we have tamed it. We can conduct, we can lit fire in a controlled manner, so much so that untrained operating staff, all the ladies and gents in my house, it is not just ladies, the gents also, me, my wife and my son. Right now we are three in the house. Each three of us, we handle fire every day in the house. Okay, we are untrained staff. We were never trained, in fire technology, but by experience, and our mothers passed on the experience to us, we have learned that how easily we can tame fire. But if accidentally we do something wrong, or there is a there is an unfortunate incident, see, maybe 1 in 1 lakh cylinders will leak, and if my house happens to have that cylinder, and it is my bad luck, but it will happen. Of course, there are ways to bring down the number of these accidents. So similarly in nuclear power also, uh, now we are operating nuclear power reactors for more than 50 years, more than 5,000 reactor years of operation experience world over. India itself is having 550 reactor years of operation. We have learned so many things, but in these 5,000, more than 5,000 reactor years of operation, there have been only 3 nuclear accidents. One is 3 Miles Island, second is Chernobyl, and third is Fukushima. If we compare these three, in the first and the third one, no lives were lost. In the first one, 3 Miles Island, no life was lost. In the third one, also Fukushima, no life was lost because of the accident in Fukushima reactor. Okay, in the first one, no radioactivity or radiation leaked out of the reactor. Something accident happened, but everything remained contained inside the reactor. In case of Fukushima, radioactivity came out, radiation came out. Okay, even today it is coming out, but it did not explode. Okay, so if we put them in order of magnitude, 3 Miles Island, I would say one of the least, a reactor where no fallout of radiation, radioactivity was there, no death was there. In Chernobyl, no death was there, but there was fallout of radioactivity and radiation. In Chernobyl, there were death also, and there was fallout of radioactivity and radiation also. So this is the analysis of these three reactors. Now, why this difference was there? The difference was there in the first one, it was a beautifully designed reactor at 3 Miles Island. So though accident happened, but the reactor design was so fantastic that the fuel melted and the entire fuel, it sat inside the reactor only. It never came out, no radioactivity came out. It is because of the beauty of the design of that reactor. Chernobyl, why this much damage happened? Chernobyl type of reactor, I think during my lecture also I mentioned about graphite as a moderator. So this is one of those reactors which used graphite as a moderator. But even otherwise, the physics design, it was a very bad design. In fact, in India, I think our Atomic Energy Regulatory Board, even without Chernobyl accident, they will not allow us to build that kind of reactor. It is we can call it an inherently unsafe reactor. So I don't know how the USSR, of course, that time it was not just Russia, it was USSR, how that kind of reactor was allowed to be made. And then the operation also, in the operation, they were doing some unauthorized experiment. They also have their regulator. So that regulator did not follow the rules, the regulation rules. And they did an unauthorized experiment, because of which there was a sudden increase in the power of the reactor. And you see what happened. Fukushima, the problem was, it is a beyond design basis accident. Now, what do you mean by beyond design basis? That the designer of the reactor, he will always take that in this place, the temperature will go up only up to this. The water level will go up only up to this. The speed of the air, the wind speeds can go only up to here. So based on certain parameters, the design is done. Okay, but some incidents happens which is beyond design. So what happened, that the water level in that area, the flooding level was much beyond what the designer had taken into account. So because of that, water gushed into the reactor, complex, not in the reactor building, reactor complex. And normally to tackle this, then there is something called, I am not telling that in India the common sense is very high. In this particular case, I am telling that we have always a provision for emergency power supply. See, in your house also it will be there. Normally you are depending upon electricity in your house. Okay, but suddenly if the electricity goes.
Sir, kindly unmute your mic. Your mic has been mute. Sir, kindly unmute your mic.
Only in emergency. So you need to keep it at a place that even in dark, you will be able to find it. Night 9 o'clock, the electricity goes. And at that time, if your mother starts wondering, yes, I know there are 3 torches in the house, but I am not able to remember where I have kept them, then it is of no use. So whatever you have kept for emergency use should be easily available. It cannot be, you can't keep emergency light in the inside the cupboard, or maybe where you are keeping gold jewelry. Along with that, you can't keep the torch. Torch should be in the drawing room, in the kitchen. One torch in the drawing room, one torch in the kitchen. So unfortunately, in this Fukushima, they had the diesel generator for emergency use, but it was put at the ground level, the lowest level available there. So when the flooding occurred, that also got submerged along with water. Now, to differentiate, in India, what we have done, in India, we also have a diesel generator plant in Tarapur 1 and 2, but it is kept at the 3rd floor level of the plant. It is not at the ground floor level. So suppose A similar situation arises in India. Water, if it comes into our reactor complex, our diesel generator will not get submerged. So these are the, there is another part of your accident. You are talking about the coming out of radioactivity, and particularly you are worried about the radioactive waste. So here, in fact, again, I would like to give you a comparison that there are things called harmful or hazardous. So there are certain potential hazards, and there are some things called real hazards. Okay. To stand on the parapet wall of 3rd floor is more hazardous, or lying on the bed in the house is more hazardous? Tell me. Naturally, standing on the parapet wall of the 3rd floor is more hazardous. But count the number of accidents. How many people fall from the 3rd floor of the parapet wall, and how many people fall from the bed? More number of people fall from the bed. Okay. Ultimately, so naturally, when children are there and old people are there, so even the bed is not safe. So we design the bed in such a manner that the child or the old person is not able to fall from the bed also. Though it is relatively safer. See, for example, if I fall from the bed, probably nothing will happen to me. You fall from the bed, nothing will happen to you. So again, there is a question. Though potential hazard is more in the 3rd floor, but the number of accidents are more in the lower hazard. So the real hazard is our beds, not the 3rd floor parapet. So similarly, I am telling you, I can give you umpteen number of examples. There is 2 chemicals, I will take the name, sodium chloride and potassium cyanide. Okay, what is sodium chloride? You and me, everybody is consuming it every day, the common salt. Okay, then what is the other chemical? Potassium cyanide. It's a poison. Nobody has been able to tell what is the taste of it, because the moment it touches the tongue, the person dies. So he is not even able to tell what is the taste of potassium cyanide, because they say somebody had wanted to write the taste, so he could write only S, and he died. So now you don't know whether it is sour, it is salty, it is sweet. You don't know what is the taste of KCN, potassium cyanide. Now, in the real life, see, let me tell you, I am 67 years old. When I turned 40, 27 years back, and I went to my doctor never asked me about potassium cyanide, but he asked me about sodium chloride. He inquired how much sodium chloride I am consuming. And he immediately told me, no, Mr. Malhotra, you are consuming beyond the limits. So I think you stop eating. See, there are certain essential items. I have to eat the vegetables, the pulses. So he told me, don't eat papad. Don't take pickles. Don't eat chaat. You go that pani puri and all that you don't eat. Make simple dal in the house, put less salt, reduce the quantity of the salt. If you want to live long, you have to reduce the quantity of salt you are consuming. So that means in my case, and in everybody's case, when you become more than 40, generally, they say more than 40, you should become more conscious about your health. So more than 40, you have a threat from common salt. You don't have a threat from potassium cyanide. Potential hazard is potassium cyanide, not common salt. But real threat is from common salt, not from potassium cyanide. What is the reason? Potassium cyanide is isolated from public. Suppose I want to have even 1 milligram of potassium cyanide, nobody will give me. I am supposed to explain why do I need it. And only after establishing the need, that what for cyanide is needed, somebody will give me, and I have to do proper accounting for that. But salt, a 4-year-old kid can go with money to the nearby shop and bring 1 kg of salt. Nobody will ask him anything. If he can utter the word, give me salt, the salt will be given. And that is the problem, because salt is easily available, so we are consuming it every day. So it has become the real threat to us. So similarly, now I want to tell you, in case of nuclear industry, the nuclear waste is very, very hazardous. It is like cyanide. If it goes into the public, it will kill public. Okay. And carbon dioxide is like common salt. So it is available in the atmosphere. It is so much. In fact, it is essential also. All our food we are eating, basically, the plants are preparing the food from carbon dioxide. All the carbon dioxide is converted into the carboxylic group by the plants. And that is how we get the carbohydrates. And then some of these carbohydrates will get converted into proteins. And also all that biochemistry happens inside the plants. Okay, so CO2 may be essential in certain quantity, only enough for the plants to absorb. But what we have done, we have increased the concentration of carbon dioxide. So just like common salt, our carbon dioxide availability around us has increased so much that it is threatening our very existence by causing global warming. So today the concern, though nuclear waste is definitely more hazardous as compared to carbon dioxide, but I think today we must concentrate how to tackle the problem of carbon dioxide. Because in case of nuclear waste, there is a technology. We are able to isolate the nuclear waste from the public. I, as a atomic energy person, I am ensuring that in your life, you will never be able to see nuclear waste, how it looks like. You will never be able to see. But of course, you are breathing carbon dioxide every day. You are in the vicinity of carbon dioxide. And let me tell you very vehemently, this topic is very close to my heart. So though doctor has suggested me not to shout, not to speak in high volume, but very vehemently, I want to tell you, if life is going to extinguish on the earth on some day, either it will be because of the war going on and somebody will drop atom bomb on somebody. Right now, that situation, I mean, some foolish people are fighting a war. I am very much against it. So in the wars, anything can happen. Chemicals will kill, atomic energy also will kill. But if there is no war, and the life will become extinct on this earth because of carbon dioxide, not because of radioactivity, not because of radiation. Okay, so please note this, that there is technology available in case of nuclear waste, in case of radiation, we can contain them. It will not come out of the reactor. If we properly design and properly operate things, there is guarantee that this radioactivity, etc., will not come out. While in case of carbon, if you burn carbon, there is only one place. I mean, there is only one chemical which will be produced. It will be carbon dioxide. And that carbon dioxide, presently at least, it has only one place to go. That is atmosphere. Though people are working, some people are working on that, how to convert carbon dioxide into some useful chemical so that it can be converted into some other chemicals, and that so that we can use the carbon dioxide. But presently, carbon dioxide is only causing problems. Okay, I think I spoke too much, but probably I'm clear.
Thank you so much, sir. It was such a delight to listen to you with your analogy, especially of the bed and the parapet, and also sodium chloride and potassium cyanide. I don't think any of us are ever going to forget the difference, the risk that a potential hazard has, and a threat, which is more common but can be more dangerous. And I think the key word that you mentioned was relatively safe. They're both dangerous, but relatively, which one is better? Right. That brings us to the end of our question and answer session. Thank you so much to all the students for your questions. Due to paucity of time, I am left with no other choice other than asking. We will put in all the questions. We will collate it. We will give it to sir, and sir can pick and choose the questions that he can answer, and then we will put it up on our website, because all
send the questions to me. I would like to see these 8-9 questions. I know there are close to 200 children. They will be having questions. So please send their questions by email to me. I will answer them.
Definitely, sir. We will be doing that. So all of you, don't worry. We will save all the questions that you have. We will send it to sir, and then we will post the answers on our website as and when sir gets time to respond to them. All right, sir, thank you so much for spending time with us. We know
Thank
you're
you.
extremely passionate about the field of atomic energy. And like I said earlier, we hope to see you speak to us about the various advancements in the field in the near future. Thank you so
Sure.
much for joining us, sir.
Yeah, thank you.
Students, I would
Thank you,
request
everyone.
you.
Good night.
Good night, sir. Students, I request you to stay back because I have a quick announcement to make regarding your final exam. Before we move on, please, I would request you all to take the time. I would give you about 5 minutes now to log on to our website on Google so you can review us. I'm sure all of you know how to review on Google. Please type in VSSF on your Google browser, and then you will have the review option. There were options with stars. I will also be showing it to you. So one being the least, you liked it the least, and 5 being the best that you enjoyed these sessions. And we'd also like your feedback so that we can ensure that our sessions to come in the future are more relevant to you. They cater to your needs. We would be happy for critical feedback as well, so that we can grow and produce better content. All right, so I'm going to give you 5 minutes now to quickly review us on Google, and then we move on to the examination dates and announcements. So this is what it's going to look like if you type in VSSF on your Google browser. You will see the review option here. So kindly click write a review. You can rate us based on the number of stars, 5 if you enjoyed the session completely, 1 if you didn't enjoy it at all. And then you can type in 2 or 3 sentences based on how you found our resource person, so that we can share the feedback with our resource people as well, so that they can also see how y'all felt during these sessions. And then you can click on post. If you have finished, kindly indicate. I know some of the questions in the chat box are if you have already. So the sessions that you've reviewed would have been with a previous resource person. Today's session was a different resource person, which is why I'm asking you again to review us today. All right. And your exam is on the 5th and 6th of March, very soon coming up. Few more days to go, between 10:30 and 11:30 a.m. We at VSSF wish you all the very best for your spot final exam. I'm sure with the way you have been listening in. Sorry. Yes, so like I was saying, your final exam would be on the 5th or 6th of March. You can take it on either dates between 10:30 a.m. and 11:30 a.m. Here's wishing you all the very best from the Vikram Sarabhai Science Foundation. We hope all of you do well, and I'm sure that you all have been preparing very diligently. So thank you so much. Thank you for all the time that you've spent with us over these 5 sessions, and we hope to see you soon. Have a good evening.